Hi, welcome to Keys Pre-Calculus. This is section 2.5 in your book. I just wanted to go over an example, go over a couple definitions and example. The first thing I wanted to review the linear factorization theorem. It says if f of x is a polynomial of degree n, where n is greater than 0, that function has precisely n linear factors. In other words, f of x can be written as a, some leading coefficient times x minus c1, x minus c2, x minus c3, all the way down to x minus c sub n, where c1, c2, c sub 3, and c sub n are complex numbers. So basically you can take any polynomial and factor it down to linear factors. However, not all of those linear factors are going to be real numbers. They could be imaginary, and they may not all be rational. They could be irrational. But you may not want to write your polynomials as with factors that are irrational or imaginary. So you could write them with quadratics as well. So there is a rule that says every polynomial with degree n greater than 0 with real coefficients can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. It's possible to do that. A quadratic factor that has no real zeros is said to be prime or irreducible over the reals. For example, x squared plus 1 is a quadratic that cannot be factored into real numbers. And it cannot be factored into linear factors that have real coefficients, in other words. So it is prime or irreducible over the reals, but you can factor it completely if you use imaginary numbers. Don't forget that complex numbers come in pairs. They come in complex conjugates. And to get the square root of -1, if you were to try to solve this, that would be I. So you could reduce this into x plus I times x minus I. And if you were to FOIL that out again, you would get x times x is x squared, negative xi, positive xi cancel each other out, and I times negative I gives you the opposite of I squared, and since I squared is -1, it would be the opposite of 1, or opposite of -1, which would be positive 1. So even though x squared plus 1 is prime or irreducible over the reals, you can reduce it completely by using imaginary numbers. Don't confuse this by a quadratic being irreducible over the rationals, however. This quadratic here, x squared minus 2, you can reduce it over real numbers. It can be written as two linear factors with real coefficients, but just the coefficients are not rational, they're irrational. This can be rewritten as x plus the square root of 2 times x minus the square root of 2. You can use that using the quadratic, or you can do that just by solving for x. But just understand that x squared minus 2 is factorable, but it's not factorable over the rationals. It's factorable over irrationals. Actually, both examples are factorable, but just not necessarily factorable over the reals, or irreducible over the reals, or irreducible over the rationals. I'd like to do example 5 in the book with you now, just to show you an example of how this works and what they mean when they ask for that. If you look on page 138 at example 5, it says to write this polynomial in part A as the product of factors that are irreducible over the rationals. So that's exactly what we're going to do. We're going to treat this as a quadratic. Even though it's to the 4th power, it is in the form of a quadratic, so we're going to try that. We're going to factor it like a quadratic. So this becomes x squared minus 5 times x squared plus 4. So I factored x to the 4th minus x squared minus 20 into x squared minus 5 times x squared plus 4. I can't go any further in the real number system. I can't factor 5 because, well, I could go in the real number system, but I couldn't go rational because 5 is not a perfect square. And 4 would not give me a real number. So part A is factored into factors that are irreducible over the rationals. Part B asks us to factor it as a product of linear factors and quadratic factors that are irreducible over the reals. So I can take this first one and I can factor it even further. It is a quadratic, but I can factor it as if that was a difference of two squares into two irrational products. X minus the square root of 5 times x plus the square root of 5, because the square root of 5 times the square root of 5 gives us 5, right? And then x squared plus 4. But there are no two numbers that I can multiply, no two real numbers that I can multiply together to give me, or no two real linear factors to multiply together to give me x squared plus 4 as its product. So in this case, part B has been factored into both linears and a quadratic that are irreducible over the reals. So I've gone as far as I can go in the real number system. Part C tells us to write it in completely factored form. Well, I cannot factor this first or second linear even more, or linear form even anymore. So that is as factors as it can be. It's irrational. But this one I can factor over the reals. This becomes a complex conjugate. X plus 2i times x minus 2i. If you remember, when I factor those, or when I multiply those out again, x times x is x squared, negative 2i plus x plus positive 2i, x cancel each other out, and then 2i times negative 2i ends up being negative 4i squared, which becomes positive 4. So on part C, you see that we have factored out the entire thing completely. So it's over irrationals and over the complex number system. So if you don't like doing that, then you could have just left it as part A as a factor of two quadratics. But you were following directions. So part A gives us factoring over the, or irreducible over the rationals. B is irreducible over the reals, and C is completely factored. And that's what it means. And you're going to have some problems in your homework that are like that. And I just wanted to show that to you as an example. Now let's look at example 6 on page 139. It tells us to factor this polynomial given that one of its zeros is 1 plus 3i. Now we know that complex zeros come as conjugates. So if 1 plus 3i is a 0, then 1 minus 3i is a 0. So we have two of our factors. One of them is x minus 1 plus 3i, and the other factor is x minus 1 minus 3i. When I multiply this out, I get x squared minus x times 1 minus 3i minus x times 1 plus 3i. And then I multiply the last terms together, and they are complex conjugates, so that ends up being 1, or I should say plus 1 plus 9, which is going to give me 10. And when I simplify this, I get x squared minus x plus 3ix minus x minus 3ix plus 10. Now, the negative 3ix and the positive 3ix end up canceling each other out. So I'm just going to cross them out here. Oops. Sorry, my pen is not working right. And then when I collect like terms, I end up getting x squared minus 2x plus 10. That is one of the quadratic factors of this original polynomial. And I can find the other factors, or another factor, by using long division. Now I'm going to take this factor, x squared minus 2x plus 10, and I'm going to divide it into my original polynomial to get another factor. So to turn x squared into x to the fourth, I have to multiply it by x squared. I'm going to put that up here on top of the 6x squared. X squared times x squared gives me x to the fourth. X squared times negative 2x gives me negative 2 x to the third, and then x squared times 10 gives me plus 10x squared. Now I'm going to be subtracting, so I'll change all my signs. Make that a negative, this a positive, and this one a negative right here. And so that gives me x to the fourth minus x to the fourth gives me 0. Negative 3x plus 2x to the third gives me, negative 3x to the third minus 2x to the third is negative x to the third. And then 6 minus 10x is negative 4x squared. And then I bring down the 2x. So plus 2x here. So now I need to figure out how I can turn x squared into negative x to the third. I do that by multiplying it by negative x. And I'm going to put that over the x term here. So negative x times x squared gives me negative x to the third. And then x times negative x times negative 2x gives me positive 2x squared. And then negative x times 10 gives me negative 10x. I'm subtracting, so once again I'm going to change my signs. Whoops, make it there. Make that a plus. Draw my line. And when I subtract, I get negative x to the third plus x to the third gives me 0. Negative 4x squared minus 2x squared gives me negative 6x squared. And then 2x plus 10x gives me 12x. And I'm going to bring down, to 60, so plus 60 right there. Now I have to turn my x squared into negative 6x squared, so I multiply it by negative 6. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 2x is positive 12x. And negative 6 times 10 is negative 60. And when I subtract all these, because the signs are the same, I should have made that a minus 60 because it was a negative 60 up there. I get my remainder as 0. So we see that it truly is a factor, and now we find the other factor. We have found the other factor. So we now know that all of the factors of the original polynomial are x minus 1 minus 3i times x minus 1 plus 3i and x squared minus x minus 6, which factors into x minus 3 times x plus 2. And it said it needed to find all of the zeros. So zeros happen when x is equal to 1 minus 3i, 1 plus 3i, positive 3, and negative 2. I hope this rough recording has helped you understand a little bit better what to do in section 2.5.